A lot of the different series that we deal with, there really isn't much to them, except to say converges or diverges because it's this type of series, and this is the reason why. All right. But just like some of the other ones, we're going to go through the process of identifying characteristics. Basically, we're going to discover the rules. All right. So instead of just being told the rules, we're going to understand why the rules work the way they do. So the directions here say use the integral test to try to figure out what values of p would cause the p series to converge. All right. So a p series is always in this form, 1 over n to the p power. All right. So if you're looking at 1 over n to the p and just thinking of a function equivalent, you might come up with something like 1 over x squared or 1 over x to the 1/2 or something like that. Now, if you're using an integral, you might say, oh, well, that's not bad because taking the antiderivative of one of those is not difficult. But we only need to do it once because we discover the rules. And then once we identify something as being a p-series, identifying just the power, whatever the p-value is, will determine whether it converges or diverges. All right? So the integral test. Well, we know that there's an equivalent function. Not an equivalent function per se, but a function that can be used to approximate the area. It's overkill, but it gets the job done. So 1 over p is our first challenge here. 1 over n, sorry. 1 over n with the p-value being equal to 1. All right, that's our first challenge. All right, that's called the harmonic series. It's good to know, I guess.
This is kind of a question for the last time.
Sure.
Monday night's content be on the final and unit 3, or just the final?
Unit 3 also, yeah. All right, so I mentioned, well, it had to be last night, that when you're using the integral test, because it's always going to have the same structure, you can jump like a step ahead. Instead of defining it as an integral from 1 to infinity, we can jump to the limit as n approaches infinity going from 1 to, oh, sorry, a approaches infinity. Of 1 over x dx, all right? And that's because we're using f of x equals 1 over x as an approximation for 1 over n. And that was that diagram I drew yesterday where you'd have the area under the curve, which is way overkill because we only care about really the area under each integer value. So, like I said, overkill. But if we can show that one converges, we'll show that the other converges. And also the same would be true for diverging, right? So, integrate. So the integral process is easy here because it's just 1 over x. So limit as a approaches infinity. And really, it could be a, it could be whatever you want, as long as it's just some placeholder for infinity. Let me get rid of that integral symbol. Natural log of x on the interval of 1 to a, which is going to be the limit as a approaches infinity of the natural log of a. Now, minus the natural log of 1, but natural log of 1 is equal to 0, so it goes away. All right. So if you know anything about a natural log function and structure, you'd know that this is going to go to infinity. Right? If you didn't, then you type in ln of x in your calculator and start scrolling in your table and see where it goes. It's going to get real big eventually. Natural logs don't increase at a very rapid pace, but they do increase to infinity. So this is going to go to infinity. Therefore, the sum from n equals 1 to infinity of 1 over n diverges by the integral test. And again, limit, make some statement about what characteristic of the test is what allowed you to draw that conclusion, right? All right, so what I just learned from this, and hopefully you as well, that's kind of the plan, is that if the p-value is equal to 1, the p-series will diverge. All right, so let's see what else we can come up with. Right. The general benchmarks are 1, 0, and all the intervals that go in between. So you would think negative numbers, and then between 0 and 1, and then anything more than 1. So those are good values to test. All right, so I'll do the same thing with p equals 2. But one thing I will tell you to consider is that sometimes, and I won't do this to you on a test, but it could be a trick question. If p is negative, or well, less than or equal to 0, bless you, it's not a p-series. All right, and the reason why would be something like, I'll give you a quick example. If you had something like 1 over, I'll say n to the negative second. 1 over n to the negative second need not be written in fraction form. Okay? That's the same as n squared. Right? So you're taking something that is a ratio and making it into a power function, or at least something that could be equated to a power function. Right? So two different things. So that takes values less than or equal to 0 completely off the table. We don't have to worry about them. But we do have to worry about these values at minimum. So let's take a look at the next one. The sum from n equals 1 to infinity of 1 over n squared. All right. So again, we're using f of x equals 1 over x squared. So limit as a approaches infinity, going from 1 to a, 1 over x squared. And actually, let me not do that, because 1 over x squared is the same as x to the negative second. I'll just write that in dx. Save myself a little step there. All right, so increase the exponent by 1, divide by the new exponent. So negative x to the negative first, going from 1 to a. Be the limit as a approaches infinity of negative 1 over a minus negative, so plus 1 over 1, so 1. With the integral test, we're looking for a finite value. Get a finite value, we're good. You don't, it diverges. All right. So in this case, it's going to converge to equal 1 because plug in infinity for a here. Negative 1 over an infinite value is going to get very, very close to 0. So the closer you get to infinity, that moving target infinity, the closer the result will get to 0. And then 1 is a constant, limit of a constant is a constant. So 0 plus 1 is 1. All right. So we can draw the conclusion that going from 1 to infinity, the p-series 1 over n squared converges by the integral test. And that's because the limit exists. All right, so looks like for values bigger than 1, the p-series will converge. All right, well, that's a working hypothesis. All right, I mean, I don't really have much to go on. I didn't try p equals 3, p equals 10, p equals 20. All right, at some point, you're just going to take some things on faith. But it's a reasonable hypothesis. If you wanted to test it further, you could test it further. Or you could take my word for it and just know that piece of information. We'll fill out that table in a second. But let's see what happens for values that are less than 1, but bigger than 0. All right. So we're going to use f of x is equal to 1 over x to the 1/2, which would be the same as x to the negative 1/2. So the corresponding limit as a approaches infinity, going from 1 to a of this increase the exponent by 1, divide by the new exponent. So dividing by 1/2 is the same as multiplying by 2. So 2x to the positive 1/2 on the interval of 1 to a is going to give me a limit as a approaches infinity of really 2 radical a minus 2. All right, radical functions, I mean, in a lot of ways, they're very, very similar to log functions, at least in terms of the shape. They have an increasing rate of change initially, and then they seem to level off horizontally, all right? Forever increasing, though, that's the important piece. So, therefore, oh, well, actually, I never really stated the limit. It's infinity. So our conclusion would be that this particular p-series (1 over n to the 1/2) diverges by the integral test limit equals infinity. So any non-finite value is going to lead to a diverging situation. All right, a lot of work. You know, if I'm introducing a new test, a p-series test, you wouldn't want it to rely specifically on something that we've already learned. You know, like what at minimum, this is good practice with the integral test, which is another test you need to know. But the conclusions here are what are the most meaningful. And what we're getting from this, first off, I talked about this above, is that any value that is less than 0, any p-value less than 0, less than or equal to 0, not a p-series. All right. So this test would not apply. All right. So if you get a p-value less than or equal to 0, you got to do something else.
If this is the exact form of 1 over n to the p, do we have to show the work? We just say
No, that's the whole point. Yeah. Yeah. Once you have this table completed, you see a p-series on a test, you'll see the examples that follow. You're going to say converges or diverges because of the p-series test, and this is why. All right. You're not going to do any of the work that we showed. All right. So why do we do all the work? Because there could be a question that says, using the integral test, you know, But I wouldn't, personally, it's not my style to make you use the integral test for something that could easily be done with another test, like the p-series test. Right? I will only make you use the integral test when an integral test is really the most efficient or only way to go. Right? So another possibility here is that the p-value is between 0 and 1. Series diverges. If the p-value is greater than 1, then the series converges.
Is infinity greater than 1?
Infinity is greater than 1, but the p-value is referencing the exponent in the original series.
Oh, okay. Oh, so it's the p-value, not the answer.
The p-value, exactly.
Now that we have these rules, if we have a p-series on the test, do we have to write out all the work? Or can we just like-
You just say it.
It is that one.
Is that one? Yeah, so that's what this next example is. Instead of going through all this stuff, what I would first do is clean this up algebraically. Algebra is your best friend when it comes to stuff like this, because you may look at this and say, well, okay, cool. We're talking about all this p-series stuff, and then you throw us something that isn't a p-series at all, but if I clean it up, I'd be looking at 1 over n times n to the 1/2. Keep the base, add your exponents. All right, so this would converge. So converges by the p-series test. P-value is greater than 1. Whole lot easier than doing the integral test. Right. Now I even showed I showed all the work with the algebra here. I mean, you could have just jumped from here to there, or you could have circled that, drew an arrow to it, wrote n to the 3/2, and then wrote converges by the p-series test. Right. So. Yeah.
And does the numerator matter as long as there's no variable in it?
The numerator, as long as there's no variable in it, yeah, exactly. Now, if there is a variable in it, it still could be p-series. You just might have to clean it up. So if this were n, let's say n squared over, keep the base, subtract the exponents, and then clean it up from there. All right. It's when you start having sums and differences, that's when you might have to do a little bit more work. So, for example, in this case, if it said n plus 1 on top, that would actually break up into 2 separate p-series. All right, so if it were n plus 1, you would have 1 over n to the 1/2 plus 1 over n to the 3/2. But the one that diverges would override the one that converges. All right, so if it was a case where you broke it up, if one ratio would diverge, then the whole thing diverges. All right, the same idea with limits. If one part of it doesn't exist, then the whole thing doesn't exist. All right. The direct comparison test, or the DCT. This is one of 2 types of comparisons that we'll get into. One is the direct comparison test, and the other is limit comparison test. They're both reliant on what I call, I don't know, I've never seen this term before, so I think I coined it, the parent EBM. All right, EBM, I didn't coin that part of it, and I didn't coin parent either, but putting it together, that's me. All right, so the parent EBM is the parent function of the end behavior model of whatever the function is you're dealing with. So I'll take you through that process in a second, and hopefully it'll make perfect sense. And if it does, then we'll be off to the races, and you're not gonna have a problem. All right. So 2 things. a sub n has to be greater than or equal to 0, and b sub n has to be greater than or equal to 0. All right, so they have to be positive values or non-negative. All right, so the question would be, okay, where's this b sub n business? Well, b sub n in one case is going to be the parent EBM of the a sub n, and vice versa for the other situation. Right? The idea is that we're looking at consistency in convergence. Right? So the first part of the direct comparison test tells us that if the sum of b sub n converges, and this relationship is true, a sub n is less than b sub n, but they're both bigger than 0, then the sum of a sub n would also converge. All right, and this has to do with the end behavior model and how it applies to limits. So if you think about, well, I was going to say, if you think about when you learned about end behavior models and limits, it's like yet another thing that may not have happened. Basically, I'll get to the idea of end behavior in a second, but a function behaves the same way as its end behavior model for extreme values of x. Right? So if you know what the end behavior model is, often a simpler function, if you can study what's happening to that for very large values of x, so as that goes out to infinity, then you can draw conclusions about the function itself. All right. If a sub n diverges and a sub n is trapped between 0 and b sub n, then it's basically going to force b sub n to diverge also. All right, so I'm gonna create some function-related diagrams. So let's say we have f of x and g of x. Now, the relationship here is that, sorry, I didn't mean to put an and symbol there, because yes, I'm going to have f of x and g of x, but I want the relationship to be that f of x is less than g of x. All right, it could be less than or equal to, but I want to specifically show the case where it's less than. All right, so there's a bunch of different possibilities or different ways that this can play out, but I do know that f of x has to be smaller than g of x. So there's my f of x. And let's say here is my g of x. Trying to make it look somewhat decent. And actually, yeah, I was going to say, let me take the arrows off of it, but I don't know. So there's a couple of ways that this can play out. One would be if g of x is converging on a particular value. Right? If it was, then f of x would also have to converge on that particular value. Right? So let's say g of x is going to eventually work its way back down to the x-axis. And converge on that x-axis. F of x, since it has to be less than g of x, it can't just blast through g of x. It has to forever be contained between g of x and the x-axis. So while it might have wanted to increase without bound, it has no choice. It has to turn around and run parallel to g of x, at least for extreme values of x. All right. Now another possibility is that maybe g of x diverges. Maybe it doesn't settle on a particular value, so it shoots on up to infinity. If that's the case, I can't draw any conclusion about f of x. All right. So it is possible that f of x diverges also, goes up to infinity. But it's also possible that it could turn around and hit the x-axis again. on its own, not because it's trapped between g of x and the x-axis like the squeeze theorem, but because it was naturally going to do that anyway. All right, so the possibilities are it could go up here, it could come over in this direction, it could go down there, it could do that, but it could also travel down its original path. All right, so if g of x diverges, we can draw no conclusion about f of x. But if g of x converges, then f must also converge with it, all right? Because it is contained. It's basically sandwiched between g of x and the x-axis in this case, all right? Whereas in the other case, we're talking about a sub n, well, oh, this is still a relationship here. But if we're saying a sub n diverges, and it's trapped between 0 and b sub n. So it's still the same relationship. But I'm changing my perspective a little bit. What I'm doing now is I'm saying that a sub n, which is going to be my f function, it definitely diverges. G is above it in some capacity. I don't know where, but I know it's living above it. If G is going to continue to be above F, and I know that F diverges, there's no way that G can go through F, so it must also diverge. All right. So that's really what this is saying in function form. It's not really, like in terms of diagrams, bless you, it's not like a work of art. But basically the idea is that it's telling us that you have basically an impenetrable barrier. This is telling us that we can't go through it. So what are the different options? The options are, well, if we know that one is going to converge, the outer one is going to converge, then the inner one must also converge. If the inner one is going to diverge, then the outer one must also diverge. All right. So that's a little bit of the conceptual stuff, but we need to get into the practical aspects of it, like this whole parent EBM. So let me give you an example of how to find an end behavior model. So end behavior model. So let's say you have a function f of x is equal to, it doesn't matter, x cubed minus x squared over x to the fourth plus x cubed. There's a bunch of different ways to find this. One way actually involves finding a limit, but I don't like that way because I feel like it's using a limit to explain a function that is then in turn used to explain a limit. I don't like it. An end behavior model in its simplest form is really just the ratio of the terms with the highest power in your function. All right. So when we're finding limits, we're often using concepts related to end behavior model. All right. In this case, we're actually just coming up with a function. We're not applying a limit. So I would have y equals x cubed over x to the fourth. So my end behavior model, my EBM, would be 1 over y equals 1 over x, if I simplify that. All right. Now, what we get from this when we're talking about end behavior models is the idea that for extreme values of x, this function and this function are going to behave the same way. So the limit of this as x approaches infinity will be the same as the limit of that as x approaches infinity. So then I would ask you, which one would you rather work with, that or that? First or second? Awesome. Let the record show that they were all thinking second, even though nobody opted to use their vocal cords. So the end behavior model is very important. Now, here's another example. Let's say I have f of x, I'll go g of x this time. G of x equals 2x squared minus x over x to the fourth minus x cubed. Again, ratio of the terms with the highest powers. We'd be looking at y equals 2 over x squared. Well, I'll write the intermediate step. 2x squared over x to the fourth, which would give us an EBM of y equals 2 over x squared. All right, so still EBM, but we need the parent EBM, so the parent function of that. The parent EBM is going to be y equals 1 over x squared. All right, the parent EBM, or the parent function, is whatever you would get if you strip away all transformations. All right, so if you had a function like y equals x squared plus 6x plus 9, all right, parabola. The parent of a parabola function is y equals x squared. Linear function, y equals 3x minus 2. The parent of a linear function, y equals x. All right, you're looking for the you're looking for the alpha, the first function related to a particular category. So y equals 3 times the sine of x squared minus pi plus 4. The parent of that would be what? What's the simplest way to express that function? I don't know if I heard it. I heard like, maybe, kind of, sort of. All right, what function did you hear out of all that? I said y equals 3 times the sine of 2x minus pi plus 4. What function did you hear in there? Do you know what a function is? We have linear functions. We have quadratic, cubic, quartic function, radical functions, trig functions. What kind of trig functions? Sine, cosine, tangent, secant, cosecant, cotangent, inverse sine, inverse cosine, inverse tangent. Which one did I say again? Sine, thank you. All right, so that would be the parent EBM. All right, and just to finish it, we have exponential and log functions. All right, and hyperbolic everything. So you're stripping the function down to its parent. So in a lot of cases, there isn't really much work you have to do to identify that. All right. What you do need to do is identify the relationship between that parent EBM and the function that's given to you. All right. Because just like with limits, what we're going to do is draw a conclusion about the parent EBM, because that's going to be easier to work with, and then use that to help us draw the conclusion about the function itself, in this case the series. All right, so what we have here EBM is something that looks like it's almost, I mean, it's like right there, it's almost a p series, except for that plus 1. If you're using the integral test, you look at it and say, okay, well, that looks like it might be fun. If only that 3 were a 2, then it would be an arctangent, but it's not. All right. So what I'm going to do is I'm going to strip it down to its base components. The term with the highest power, top and bottom. All right. So I'm looking at this series from n equals 1 to infinity of 1 over n cubed. All right, so look at our conditions here. We have possibilities, a converging, diverging business, that's all wonderful. But one of them is going to be the parent EBM of the other. It's just, I don't know which one is going to be the A sub n and which one is going to be the B sub n until I really get to work on this. All right, so what I'm going to do is evaluate this parent EBM and determine whether it converges or diverges. That's going to put me in one of these two categories. then I'll have the size relationship. I'll just have to verify that size relationship, and then I'll be good to go. All right. So this parent EBM, would you say it converges or diverges? Converges by what? P-series test. By PST, and specifically the case where P is greater than 1. All right, so we're in the first category, a converging situation. All right, so B sub n is the parent EBM of A sub n. So that means that this is my B sub n, and this whole shibiggity bangity over here is the A sub n. This size relationship needs to be true. That's the only other condition that needs to be in place here. If that's the case, then I can draw the conclusion that this converges also. All right, so A sub n is less than B sub n. The question would be, well, how do I know that? Well, there's two ways you could figure it out. One, by the numbers. Take some value, plug it in for n for this, plug it in for n for that, and see which one's bigger. All right. The other is, you're starting off with 1 on top. Here you're dividing by something bigger than you are here. So this fraction would necessarily have to be smaller than that. All right. I don't need you to prove arithmetic to me. All right. So you don't have to show me how you know A sub n is less than B sub n. You just need to make that statement. So therefore, yeah, well, the funny thing about this unit is they're all proof questions. You know, really, if you think about it, there's a lot of demonstrating rules. So there won't be any question where it's this is the proof question per se, because every one of them pretty much is. So another reason why it's open notes. I just remembered I didn't let my stat class have open notes last semester for the third test because I forgot. That explains something. All right, so anyway, so therefore the sum n equals 1 to infinity A sub n. Now you could write A sub n if you want. You can do a little shorthand because over here I designated this as A sub n. All right, so you don't have to write 1 over n cubed plus 1. You've already established what A sub n is. Converges by the direct comparison test. All right, so got to be careful. It's only the P-series test that told us that this one converged. We only know that this one converges because of the direct comparison test, comparing this to that with that inequality. All right. If you don't give that explanation, you know, this detail along with that, then all you've shown me is that this converges. Maybe like, yes, useful piece of information, but you haven't answered the question. All right. So what I would equate that to would be me giving you a question on a test and you saying, I don't like that question, and then changing the question into something that you did like, answering that and expecting full credit. All right, so that's how egregious leaving this off would be. All right, so for the second one, parent EBM. And you don't actually have to label a parent EBM, you just have to state what the comparative series would be. And it would be 1 over 3 to the nth. All right, the parent, exponential functions are weird because the parent function is a to the nth power. All right, but a could be any constant. So there is no preferred constant. I guess E would, if you have a choice, E would be the best one. No, that's not true. 1 would be the best one, but then it wouldn't be exponential. All right. So when you strip down all the bells and whistles, this is what you come up with. And then what you'd be looking for is a size relationship between these two, but not until you determine convergence on this. All right. And this is where things start getting a little interesting, because we learned about the p-series test a little while ago. This is not a p-series. I mean, in fact, you look at this compared to that, it's like you can see it's not the same. But you want to apply the thing that you just learned when really it's something that you learned 2 days ago. All right? And that would be the geometric series test. But at first glance, you're like, well, I don't see it, until you convert, clean it up algebraically, and write this as 1 over 3 to the nth power. You can put the coefficient in front if you want, but this is going to converge by the geometric series test, the GST. And how did I know that? What characteristic of the geometric series test tells me that this is going to converge? Study.
The absolute value of R is less than 1.
Boom shakalaka. The absolute value of R is less than 1. Right? So whatever the base of your exponential is, if it's bigger than 1, it diverges, 1 or bigger. And actually, 1 is your exception, because if the base is 1, it's not exponential, it's just the line y equals 1. But that would diverge anyway, right? But if it's less than 1, aka between -1 and 1, you have convergence. All right, so that's good. So we're still in the same territory we were in part A, where it's a convergence situation. So we know that the first series we dealt with, the one that was in question, is our A sub n. And this would be my B sub n. Size relationship is going to be the same. A sub n is less than B sub n. All right, and that's because you're dividing by more here than you are here. So this has to be a smaller fraction than that one. All right, so therefore, same conclusion. A sub n converges by the direct comparison test. All right. Next one. We have a sum from n equals 1 to infinity. Let's see, 1 over n to the 1/2. Okay, because again, we're just taking the heart of the expression, the ratio of the terms with the highest power, stripping away any transformations, so any constant multiples, any horizontal, vertical shifts, get rid of all those, so addition, subtraction within and beyond. So we have 1 over n to the 1/2. All right, so what's going on there? Diverges, p-series test. And that's because the p-value is between 0 and 1. All right, so we're in a diverging situation. So we're in the second category here. All right, A sub n is the parent of B sub n, so the roles are reversed. So we just have to ensure that the relationship is still the same, and that is that A sub n is less than B sub n. All right. So b sub n is going to be bigger because we're dividing by less here than we are there. So that's good news. We have consistency. So therefore, a sub n diverges by the direct comparison test.
Why does that one BM versus that one AM now?
The short reason is because the rule says so. The lengthier reason would involve the graphs.
Why is, under the second sigma, it says n equals 1? Why isn't it n equals 4?
Because it should be.
Difference.
It doesn't make a difference, but it should say. Just force of habit.
Conclusion, should it be b?
Should also be, oh, and b sub n, yeah. I got caught by habit. And it should, so it should be 4 and it should be b. Gotta hit record. So, given, oh, I don't like this notation issue. Like, I got caught with the equation editor. I'll take this as a typo. Anytime you see this in the package, where it's in this form, it shouldn't look nice like this. We want it beautiful. That's like, what is this nonsense? So anytime you see that, that's a typo. You can claim that. Okay. So, given that the sum from 1 to infinity of a sub n and b sub n is the parent EBM of a sub n. So the same as before. If a sub n and b sub n are both positive, and the limit of the ratio of the two is L, all right? So it's going to actually equal L? No, it's some value L, some value that exists. That has to be finite and positive specifically, all right? So not infinity, not a DNE, and it has to be positive, so no negative numbers, right? Then the two series will either both converge or both diverge, all right? So let us investigate. So it's along the same lines as the last one, where we're going to use the parent EBM and whether it converges to help us make a determination of whether the given series converges or diverges, all right? But it's not as simple as the direct comparison test, because these are much more elaborate functions, and the direct comparison test only works with simple functions, all right? So I'll get my parent EBM and I'll create that summation. So it's the ratio of the two terms with the highest power, right? And strip away all the missing, or the bells and whistles and all that stuff. So it's just going to be 1 over n. All right, because you got n to the 4th over 4n to the 5th, simplifies to 1 over 4n, but then drop away any multipliers. All right. So now this is going to be b sub n specifically. All right, the other one's a sub n. Okay, make a note of that. All right. So, a couple of things I can do to get started. One of which has to do with the b sub n. And that's usually the easy thing to do. Make a determination of whether that converges or diverges. Because when it says the two series will either converge or diverge, you're like, okay, cool, that's great. How do I know which one it is? It's all based off of what you can determine from the easier of the two series. And that's this one, which will diverge by the p-series test and that's because p is less than or equal to 1. Well, between 0 and 1, really, but All right, so we have that. So if the other aspect of this is satisfied, meaning when I create the ratio and get a limit that exists, then I can draw the conclusion that the given series also diverges. But if I go to find the limit and I get something that is infinite or negative, then this test fails. I got to do something else. All right. So I'm going to find the limit as n approaches infinity of my a sub n. So n to the fourth plus 10 over 4n to the fifth minus n cubed plus 7 all over my b sub n, which is 1 over n. Simplify. All right, just doing a little keep change flip here. Multiply by n over 1. We're going to get the limit as n approaches infinity of n to the fifth plus 10n over 4n to the fifth minus n cubed plus 7. And really what we're trying to do here, and this is the way the limit comparison test works, is by dividing by the end behavior model, you're manufacturing a common degree between the two parts of the fraction. So we had a power of 5 on the bottom. We will now have a power of 5 on the top, which allows us to get a finite limit. All right, if that didn't work out, if you were unable to do that, so basically if you multiplied by the reciprocal of your end behavior model and you got, let's say, a larger degree on the top than the bottom, then that's an infinite case. Or if you got something smaller somehow, then that would be 0. That's not a positive number. That would be the case where this would fail, and you'd have to do something else. All right, so, but this ends up being 1/4, which is finite and positive. So therefore, a series, and I really don't want to write all that again, a sub n diverges by the limit comparison test. All right, and I don't have to make any additional statements there because I already said finite and positive.
Why did you divide a? How do you get 1/4 for the?
When you're finding the limit of a polynomial fraction, if the powers are the same, you're going to divide the two leading coefficients, and that's going to be your limit.
All right, thank you.
No problem. All right, so a little bit of algebra. Nothing too crazy because really you're just running through with a multiplier, but you know it's still more algebra than we had to do for previous questions. So maybe it's shocking. I don't know. All right, so parent EBM. This one's n from 2 to infinity. Again, the lower bound doesn't matter because all these sums, they really take shape as you get out to infinity. Right? So whether it starts at 1, 20, doesn't matter as long as it's going to infinity. All right? We're defaulting to the set of positive integers. So if at any point you have a negative lower bound, then that's a problem. But that's not something that could happen. All right, so 1 over n cubed. So I'm going to find the limit as n approaches infinity of 1 over n cubed minus 2 over 1 over n cubed. And again, this is my a sub n, and this is my b sub n. And again, you know, sometimes you want to actually make that note, even for problems prior to this, like p-series tests and stuff like that, just so you could take advantage of, in your final answer, saying the sum of a sub n rather than the sum of all that funny business. All right, so just something to consider. Anyway, this ends up giving us the limit as n approaches infinity of n cubed over n cubed minus 2. So I get the finite value here of 1. That's my limit. The one thing I didn't do, so I'm doing it in a reverse order, not on purpose, and just only because I completely forgot. I do have to make a determination because part of this is making or drawing the conclusion of whether they both converge or both diverge. So I found one condition. The other condition would be whether or not it's actually leading to convergence or divergence. All right, so b sub n, what's going to happen there? 1 over n to the third. Is that going to converge or diverge? Converges by p-series test. And that's because p is greater than 1. All right, so therefore, a sub n will converges by the limit comparison test. So the difficulty level of this stuff is directly related to your ability to determine convergence or divergence of your end behavior model. You can figure that out, then everything else is fine, because these are not, like, when you think of difficult limit questions, you shouldn't be thinking of something like this. Right? And also, I've been doing it by hand, but if you really don't know the limit, hit y equals, type in x cubed over x cubed minus 2, and just start scrolling in your table. Where's it going? Seems to be leveling off. Where's it leveling off? Hopefully you see we're at 0.99999. Oh wow, I'm pretty sure that's going to 1. All right, it's getting really big, like 3,000, 10,000, 180,000. This seems like it's going to infinity. All right, the table approach is the way to go if you're jammed up and you can't figure out how to do it by hand. All right, there's no reason you should get hung up on the limit part of it. Series. All right. I guess a trick question would be to put a -1 to like the second power in the series, just so you would look at the -1 and say, oh, it's alternating, but it wouldn't be because it's a constant exponent. But I'm not about that kind of thing. So -1 to some variable power indicates that your series is alternating back and forth between positive and negative. All right. So if that's the case, then you would consider / definitely use the alternating series test. But these conditions need to be in place in order for the alternating series to converge. All right? Two very easy things to verify. One is that the limit of a sub n has to be equal to 0, and also it has to be a decreasing sequence. Now, this notation is all wonderful and everything, but decreasing just means if I list out the terms of the sequence, the fractions or values are getting smaller and smaller. All right. The one little twist on this, and it's not really that much of a twist, is that a sub n is defined as everything except for the -1 part. All right. So if I look at that series, it's only the n over 2n minus 1 that's the a sub n. All right. The other part is what generates the alternating aspect of it. All right. Now, with any kind of test, you just got to be careful, because if they give you a condition that tells you one thing, it doesn't mean that the opposite is always true. So you read the notation here. It's saying if the limit is not equal to 0, you can't assume that it's definitely diverging. What it means is that you're dealing with something that could be inconclusive, all right? But I'll talk to you a little bit more about that later on, because you start getting into the nth term test rather than the alternating series test. All right, so, but for this one, we'll dive right in. The first thing you want to do is verify really that it's decreasing in size. All right, so do you want to take it on faith, or do you want to like verify it manually? Well, I'll take the guesswork out of the way. If you're applying a test and you don't verify all the conditions, then you haven't fulfilled the requirements of the problem, so you wouldn't get full credit, right? So what that means is that I need a few values for you to demonstrate. I need you to write down a few values to demonstrate that this is a sequence that's decreasing. Where you come up with those values, that's up to you, but it's not difficult to do it by hand. Even though, I mean, they look terrible, but they're not hard to evaluate, because you start off with a 1. If you plug the 1 in for the exponent, you're going to get a 2. So negative 1 raised to an even power, anything to an even power is going to become positive. All right, so that's telling me that my first term is positive. And it's alternating, which means the second one is negative, the third one is positive, the fourth one's negative. So now I'm done with that negative 1 to the 2n, I'm sorry, negative 1 to the n plus 1 power. So I know I'm dealing with a positive value. Plug in the 1 for the n, I'm going to get a 1. Plug in a 1 on the bottom, 2 minus 1 is 1. So the first term is actually just a positive 1. All right, the second term, I'm going to plug in a 2, but again, I'm going to ignore this because I already know it's going to be negative, because it has to alternate. 2 over 4 minus 1, so 2/3. And just really one more ought to do it. Next one's going to be positive. We only care about the magnitude decreasing, so don't let the signs get in the way. I'm not going to put a plus sign there. Yeah, because people would say, well, clearly a negative is less than a positive, but the next one's going to be positive. Isn't that more than the negative? We care about the magnitudes. All right, so the absolute measures. So 1, 2/3, whatever the next one is, those values. If I plug in a 3 on top, I'm going to get a 3. If I plug in a 3 on the bottom, 6 minus 1 is 5, so 3/5. All right, and so on. So I'm just going to make a little notation here that it's decreasing. All right, shorthand is fine. So 2/3 is less than 1. 3/5, that's 0.6. We're talking 0.67, 0.6. It's smaller. All right. What's that? Because if I were to plug in a 2 here, this would become an odd number. Negative 1 to an odd number is negative. Okay. And also, whenever you're dealing with alternating series, it's always going to bounce back and forth between negative and positive. All right. So we have that condition. Now, in order to determine convergence, I just need to show that the limit as n approaches infinity of n over 2n minus 1 is going to be equal to 0. All right, so again, a sub n is greater than 0. All right, so these are all positive values, assuming that we're plugging in numbers. So the only thing that would make this negative is the negative 1 to the n plus 1. So a sub n is positive, so we're good there. All right. We just established that it's a decreasing sequence. Both of these conditions need to be satisfied. Right? So it's not enough to say it's decreasing. I need this limit to go to 0 as n approaches infinity. Unfortunately, that's not going to happen. We're going to get a 1/2. All right. So that's where this little notation comes into play. 1/2 is definitely not equal to 0. What's happening here is that this series diverges by the nth term test limit is not equal to 0. All right. So that's a weird little quirk of the alternating series test. If both of these conditions are met, it converges by the alternating series test. But if this series, if this fails to equal 0, like really, if you think about what I did here, I found the limit of this a sub n value, n over 2n minus 1, which is what we would do if we were applying the nth term test. The nth term test told us that if we got a 0, that was a problem. 0 meant inconclusive. All right? Anything other than 0 meant that it diverged. All right? The nth term test is also the divergence test. All right? So we now know, because we ignored the alternating part of it, we now know that this series itself diverges. All right? So since this is a fundamental component of the given series, what I can then say is that the series going from -1 to infinity of -1, let me just clean that up, -1 to the n plus 1 times a sub n diverges. Now, it would also be by the same reason. It's the nth term test, so I don't need to write it again. All right. And I'm just using shorthand here. -1 to the n plus 1. And then all of this amounted to a sub n, so I just wrote it that way instead of writing all this stuff again. I don't want to do that. All right. So we were so close. If this ended up being equal to 0, we would say it converged by alternating series test. It's not equal to 0, but it's the nth term test that tells us that's causing a divergence. All right, so it's a very, very weird quirk of the alternating series scenario. But let's see when that actually works. All right, so the a sub n, I'll just write it off on the side here. This would be 1 over n, and so I'd be looking at the sequence. Let me do the limit part of it first. The limit as n approaches infinity of 1 over n. That one definitely is going to be equal to 0. All right. Now, in terms of the actual series itself, the expansion. If I plug in a 1, I'm going to get a negative number. -1 to the first power is -1. -1 over 1 is a -1. It's my first entry in the series, or in the sequence expansion. If I plug in a 2, that's going to give me a positive on top, a +1 over a 2. So it's definitely alternating and decreasing in size, in magnitude. So the next one would be -1 third, and so on. So it's decreasing. All right. So this one's nice because we have the decreasing magnitude of the expansion of the sequence. And we also have the limit of the a sub n value equaling 0. So this one will converge. So therefore, we're looking at n equals 1 to infinity of -1 to the nth over n if you want, or you could write times a sub n converges by the alternating series test. All right, there's no more detail you have to include in your explanation there because the detail would be you just restating everything that you've already written, and that would be overkill.
So it's just basically show that the signs change at every term, and then
First, you need to make sure the signs change. Then you also have to make sure that the absolute value of these numbers are getting smaller and smaller. All right. Once that happens, you know you're dealing with alternating series that's in the right form. then the limit occurs. You test that, make sure that that's equal to 0. If it's equal to 0, it converges. If not, then it diverges by the nth term test. Bless you. Okay, it's about that time. We'll take alternating series remainder. It's very straightforward. It's along the same lines as the approximation stuff we were talking about yesterday. It's basically the idea that once you know that a series converges on a particular value, then you would take steps to figure out what it converges to. Right? So then the question would become, is an approximation good enough? And in a lot of cases it is, right? As we learned yesterday with the approximation technique that we talked about involving the integral test. Right? So this is one that's specifically related to the alternating series, but it's kind of cool, and it also it's not difficult. Right? It requires some numerical computation, but nothing too earth-shattering. Suppose the series has terms that are alternating, decreasing in magnitude, having a limit of 0, aka a converging alternating series. If the series has a sum that we call S, then this would be the relationship that holds true. Right? But this is the important piece. You can approximate the sum by using the nth partial sum, and your error will be bounded by the first truncated term. All right? So what that means is that if I were to, for example, in the first problem, find the fourth partial sum, which would be S sub 4. Whatever the fifth value is, the fifth term of that sequence, that's going to be the amount of error that you could possibly have, the maximum error. All right? So it holds with the same idea as yesterday, where if you keep incorporating more terms, you're going to reduce the amount of error in your approximation. But here, you're actually, instead of having to use an integral to compute the amount of error, it's just going to be the next term in the sequence, right? Which is pretty easy to come by. Right? So the only issue is you have to actually come up with the sum of the first 4 terms, which is not terrible, but it's not always something you want to do. Right? So it's alternating, which means that we have to account for the fact that there's going to be a sign change. So if I plug in a 1, I'm going to be looking at a power of 1 minus 1, which is 0. So the first term is going to be positive. So negative 1 to the 0th power is positive 1. So 1 over 1 factorial. All right, the second term is going to be negative. All right, so that's going to be negative 1 over 2 factorial. Plus positive 1 over 3 factorial. Plus negative 1 over 4 factorial. All right, so we're finding the sum of the first 4 terms. So we'll have to crunch those numbers, but you know, that's not the end of the world. Now, the fifth term of the sequence, so the fifth term, so this is, I'll just make a little note, a sub 1, a sub 2, a sub 3, a sub 4. A sub 5 is going to be a positive 1 over 5 factorial. That's going to be the maximum error. All right, so this is going to be our approximation, S sub 4. And really, every partial sum is an approximation. It's just a question of how accurate it's going to be. If I were to say, all right, I'm going to approximate this series by just going out one term, you're like, okay, well, the sum is 1. All right, well, I'm going to be way off, but it's an approximate. All right? It's more like a shot in the dark, but it's still an approximation. So I just got to crunch these numbers. The recommendation is to, as you're dealing with more and more complicated situations, get the calculator involved. All right, so let me show you a little technique that I like to use. It's numerical in nature. It's a slight variation on what I showed you yesterday. Just pop it all in my calculator, or I'm never going to remember to do that on a test. Open notes test. Maybe you write down these steps in your notes. And when it comes to doing this, it's all there for you. I don't know. But you know what, like, I used to write down all the steps for my students and give like nice handouts and everything. And then I realized that people weren't paying attention during class. And so they were just waiting for me to hand them the handouts. And then I figured the added little bonus of that would be if I created a video where I was going through all the calculator processes, and that was the only way, like if you forgot to do how to do something on a calculator, the only way you can get the information would be to go to my YouTube channel and watch the video. Then I'd get more views. And then maybe you'd hit the like, thumbs up, and then I can benefit from it. They demonetized me, so I don't get any money. But now it's just a matter of pride. I didn't have enough views
Why did you want to?
because I wasn't getting enough views.
That's
Yeah. I know. It's crazy. My biggest views are like whimsical topics where it's like, oh, let me just talk about this. And I'll get thousands of views for that. Or tech assignments. Tech assignments do well on YouTube. But like regular lessons, nah. Teach an Algebra 1 class at high school. I get 1 view for each one of those videos.
you know who it is.
I know exactly who it is.
Okay, great.
He's a really good looking guy who knows a lot of math.
Is it you?
Yeah, it is me. It is me. Yeah, most people have the moment of like, all right, I'm not sure if he's talking about himself. He knows a lot of math. Yeah, possibly. That thing I got fixed. All right, so this one, I just crunched the numbers while we were talking. It's 1 over 120 slash, I've done that 1,000 times already, so I know from experience that it's 1 over 120. So what we get from this is the idea that the approximation, so first off, it has to converge. We have to know it converges on a particular number. Otherwise, what are we approximating? This is the approximate value, 5/8. And we will be off. If we are off, we're only going to be off by at most 1 over 120. Or 1/120th of a unit. All right, that's good. That's not bad at all. All right, so less than 1%. All right, what we wanted to do is have it be less than 1 over 100, so less than 1%. We achieved that because 1 over 120 is less than 1 over 100, so this is a good approximation. All right, now everything is based off of scale. So if you're talking about, I don't know, atomic mass, and I tell you that it's off by like 0.1 gram, that's probably not a good thing. Right? But if I tell you I'm talking about the weight of a car and it's off by 0.1 gram, then that's great. You know, if I'm approximating the weight of a car, I'm like, and I'm only off by 0.1 gram, I'm like that's pretty solid. Like some prior knowledge must have come into play there. Right? So it all has to do with context, but generally, the small, like if you get something less than 1%, you're in pretty good shape. So use the results to find an interval in which S must lie. So that's where we kind of generalize this. Let me do that in a different color. I'll do it in black. S minus S sub n. Now, n in this case is 4. Has to be less than a sub 5. All right, S minus S sub 4 has to be less than a sub 5 by rule. right? S minus S sub n has to be less than a sub n plus 1, and we denoted all of this to amount to S sub n being S sub 4 and a sub n plus 1 being a sub 5. Right? What this means algebraically is that S minus S sub 4 is going to be between negative a sub 5 and positive a sub 5. Now, getting particular here, it tells me that negative 1 over 120 is going to be less than S minus 5/8, which in turn will be less than 1 over 120. So if I add 5/8 to everything, I'm going to get an interval that will capture the true sum. All right, so 5/8 minus 1/120th, and so math right now, and then so 37 over 60. And 19 over 30. Bless you. All right, so the true sum has to be in that interval. And really, if you think about it, we only had to go out 4 terms in order to get a good approximation. That's pretty good. All right, you may say, okay, well, let's see if we can do better. And by better, I don't mean more accurate. I mean less accurate with an acceptable amount of variation, acceptable amount of wiggle room, right? So if I, for example, only went out 3 terms, then I will have an amount of error consistent with 1 over 24. So 1 over 4 factorial amounts to 1 over 24. So 1/24th of a unit. So you're talking like close to 5%, roughly, 4 to 5%. So if you're willing to accept an amount of error in the interval of 4 to 5%, then you would only have to compute the sum of these 3 values. Right? So if you're looking for a ballpark figure, then that might not be bad. All right? Now 5/8, like if I were to take 1, if it's just the first 2 terms, 1 minus a half is a half. 5/8 is in the neighborhood of 1/2. 4 out of 8 would be 1/2. So you're looking at 1/8 in terms of the amount of variation. So is that 0.125? So 12.5%. So even just going the 2 steps, you're looking at only 12.5% of deviation. So even that, depending on the context, may not be terrible, right? So it depends on the situation. But what this gets for us is the idea that once we have convergence, if an approximation's all you need, then there isn't really much you need to do. But if you have to come up with exactitude, then that could be a different story. All right. So I'll put a star on the next one, because it's really just the same kind of problem. Just you need to figure out how many steps you need to get in order to get an error that's less than 1 in 1,000. So that's not, in terms of increase in difficulty, it's marginal. Then we get into absolute and conditional convergence. Still living with the alternating series. All right, so we'll be done with this in a minute. Absolutely convergent if the absolute value of the series is convergent. All right, so that's the absolute part of it. It's conditionally convergent if your alternating series converges, but the absolute value of the alternating series does not. Right? So it essentially means that you have to establish 2 things. One, whether or not your alternating series converges. So we get to work on that. So if you want to use the calculator to run the numbers, you can. Or you could just plug and chug. In all honesty, in most cases, plugging and chugging is not the most challenging way to go. So a sub n here We're looking at 1 over the square root of n. The expansion of that would be 1, then 1 over root 2, then 1 over root 3. We know it's alternating, so you could ditch that step because the negative 1 to the nth establishes that it's alternating. All right. Also, determine whether the given alternating series converges or diverges. So it's really kind of letting you off the hook with that. I just need to make sure that it's decreasing, and in this case it is. All right, decreasing. Now, if I was not sure that it was an alternating series, then I might want to show the positive negative, but even that's a stretch because once you see a negative 1 to a variable power, you know it's alternating. All right, so I need the limit as n approaches infinity of 1 over, I'm going to write it as n to the 1/2. All right, and so that's going to be equal to 0. So therefore, the series from n equals 1 to infinity of negative 1 to the nth times a sub n converges by the alternating series test. All right, so that's 2 pages ago. Same skill. Pretty much the same problem. But now what I want to do is establish whether it's absolutely convergent or conditionally convergent. And all that amounts to, and it's really, well, I'll say usually, I was going to say mostly, but it's usually a fairly easy process because what I'm going to do is I'm going to find the sum of the series without the negative 1 to the nth power there. All right, I'll show the intermediate step just for this one case because the sum from n equals 1 to infinity of the absolute value of negative 1 to the nth over the square root of n. Really, if you think about it, the absolute value is not going to impact the radical because n's got to be positive based on the bounds of the summation. So square root of positive is positive. Negative 1 to the nth is going to be positive or negative depending on what n is. But if I'm telling you I'm taking the absolute value of it, then any negative is going to go to a positive. So really, anytime you're looking for the absolute value of an alternating series, all you're doing is dropping the negative 1 to the power part of it. All right. So what we get from this, 1 over n to the 1/2, is that that's going to converge or diverge? Converge, diverge, less than 1, yeah. Diverge by what test? By p-series test. And that's because the p-value is less than 1. All right, so more than 0, less than 1. Less than or equal to 1. All right, so therefore, lots of therefores in this one. That original series, negative 1 to the nth times a sub n, is conditionally convergent. Yeah, but it's the weird transition where first we're addressing the alternating series itself. So all of this stuff, let me just cordon this off a little bit. All of this is the first part. Because how could it be absolutely convergent or conditionally convergent in terms of an alternating series if it's not an alternating series that is convergent or divergent to begin with, right? So first you establish this alternating series, then get into the characteristics of an alternating series, then determine whether it converges or diverges. If it diverges, you're done, right? It's not going to be absolutely or conditionally convergent if it's a divergent series, all right? So from a student standpoint, you're rooting for divergence because that means you get to stop here, all right? So once you establish that it does converge, then find the absolute value of your original series and determine whether that converges or diverges. Whether it converges or diverges will dictate whether the original series is absolutely or conditionally convergent. All right, so if convergent and convergent, then it's absolute. If it's convergent but then divergent for the absolute value, then it's conditional. If it's divergent, or at least the original alternating series is divergent, then that's the end of it. No more work after that. All right. So the second example is very much like the first one. So I'll put a beefy star on that bad boy. So then we move on to the ratio test and the root test. And this is the last page we're going to do tonight. All right. So ratio test, you can look at it and say, well, it's got ratio in it. So series that's in the form of a ratio could be a ratio test situation. What you want to be looking for are n's that exist top and bottom, but are not nth rootable, right? So if that's the case, then what you're looking at is possibly, but I'll even say most likely, a ratio test situation. Unless the exception being that you can simplify it in such a way that it ends up being a p-series, not a p-series, geometric series, all right? So you might look at something that's very elaborate, but then it cleans up nicely to something like 1/2 to the nth power. If that's the case, it's geometric series, right? If you see a factorial in it, it's going to be a ratio test situation, all right? It's almost assuming that there's an n top and bottom, and it's not alternating series. If you see a factorial in it, it's almost always going to be a ratio test. All right? So the question becomes, well, what do? Well, the process tells you what to do. We have to find a sub n plus 1. A sub n is given to us. We have to determine what a sub n plus 1 is and then find the ratio of a sub n plus 1 and a sub n, which requires algebra. Once we do that, we find the limit of that absolute value. If it ends up being less than 1, it converges. The original series converges. If it's more than 1, it diverges. All right, so let me make a note. This is my a sub n. A sub n plus 1 is just the next term in the series, really. So I'm just replacing all my n's with n plus 1s. So 2 to the n plus 1 over n plus 1 factorial. All right. Now, recommendation, simplify this or clean it up algebraically now, and then create your ratio. So, what do I mean by that? You have a sum in an exponent. Sum could be broken up as a product of two exponentials. So instead of writing 2 to the n plus 1, I'm going to break that up into 2 to the nth times 2 to the first, or just 2. All right, again, the idea is to simplify it. So when I create the ratio, I'm going to want some things to cancel. one of the things I'm going to want to cancel is the 2 to the nth. And so by breaking that up, I'm going to make that happen. Right? There's other ways to do it, but this is the most efficient way. All right. N plus 1 factorial can also be thought of as n plus 1 times n factorial. All right, because every number factorial is the product of itself and the next number down the line factorial. So like 5 factorial is 5 times 4 factorial. 10 factorial could be thought of as 10 times 9 factorial. N factorial could be thought of as n times n minus 1 factorial. Here, n plus 1, the next number below it would be n factorial. All right, so I'm going to create my ratio in limit form. Two to the nth times 2 over n plus 1 times n factorial all over 2 to the nth. Let me make that look more like a power. 2 to the nth over n factorial. And if your reaction is, how the hell am I supposed to find the limit of this? It's a mess. Well, you just answered it. It's a mess. Let's make it not a mess. 2 to the nth is going to cancel. N factorial is going to cancel. Basically, everything that made this limit difficult cancels. Right on down to 2 over n plus 1. This is all that complex fraction stuff you did in college algebra or algebra 2. Fraction over a fraction. If you have a common factor between the numerators, you can cancel them. Common factor between the denominators, you can cancel them. It's what you would get if you did the keep change flip and then did the canceling, but you're saving yourself a step. Right. So now I have a much simpler ratio. Much simpler. That absolute value is there, kind of annoying. But we know that functions transcend limits. So I can take the absolute value out and make it the limit as n approaches infinity of 2 over n plus 1. What is the limit as n approaches infinity of 2 over n plus 1? 0. And the absolute value of 0 is indeed equal to 0. All right. So I remember when I learned all this stuff, it was a question of, okay, sometimes 0 is a good number, sometimes it's a bad number. When is it good? When is it bad? I don't know. Hopefully the test is open notes. All right, cool, it is. Right? If your limit is less than 1, doesn't matter what it is as long as it's less than 1, then your series converges. All right, so undo. I don't know why that happened. So, therefore, the sum from n equals 1 to infinity of a sub n converges by the ratio test. You have to write it out. The limit is less than 1. All right. This RT could be something else. So this is what I was talking about, I think, yesterday when I was talking about abbreviations the first time. That there are exceptions. All right, so. But ratio is not a lengthy word, so I think we'll all get over it very quickly. Right, so it's really this part of it that makes it complicated. If you can get this part of it, then you're good, because everything else cleans up nicely. So I'm going to put a star on the second one and then move to the third one. Yeah, the third one. Yeah. All right, so we have our a sub n. We need a sub n plus 1. All right, so all you're doing is you're increasing your n value by 1. Right? You could think of it as replacing every n with an n plus 1, but that just amounts to increasing n by 1. So if I were to change this by increasing it by 1, it'd become n plus 2. So n plus 2 factorial. Over 3 to the n plus 1, I almost said factorial. 3 to the n plus 1 only. All right. Now, in the process of simplifying, we hope to be able to cancel some of this stuff out. The hope specifically is that you'll cancel out pretty much all of a sub n. All right, that's what happened in the last problem that we did. Maybe you'll have a constant multiple laying around, but that's all right. Now you want to cancel out the beefy parts of it. So if that's going to happen, I want to break this up to n plus 2 multiplied by the number that's 1 less than it factorial. What's a number that's 1 less than n plus 2? N plus 1. For the exponentials, you're basically undoing keep the base out of the exponents. So 3 to the nth times 3 to the first. All right, so then all we're doing is we're finding the ratio, the limit of the ratio. So limit as n approaches infinity of the ratio. And one thing you can do if you want, I mean, not everybody wants to do this, but I'll give you the opportunity to do it. You do the cancellations on the fly. You know, if you know what part of this is going to cancel out with what part of that, then you could just go right to the simplified expression without showing all the details. Not everybody wants to do that, so I understand. So n plus 2 times n plus 1 factorial over 3 to the nth times 3 over n plus 1 factorial 3 to the nth. Cancel all that is cancelable, which should be a fair amount of it. And again, with the idea being that if you're doing it right, damn near all of a sub n should cancel out. The only thing, again, you might be off by is a constant multiple. All right, so you're left with n plus 2 over 3. All right, which amounts to the same thing as the absolute value of the limit as n approaches infinity of n plus 2 over 3, which is the absolute value of what? Infinity. Absolute value of infinity is infinity. And so we now know that this series diverges. Let me actually state what the series is. Another ratio test. And that's because the limit is greater than 1. Now, it doesn't have to be specifically infinity. It just worked out in this case. It just needs to be greater than 1 to diverge. Less than 1 converges, greater than 1 diverges. So that's the ratio test. And again, the hardest part about that one is the algebra. I found, just through personal experience, people who struggle with this one, they don't know what to do with the factorials. So if you can study that part of it, then everything else is going to work itself out, because the parts with the exponentials people intuitively have a good sense for. It's just the factorials tend to throw people off. All right, and I've seen everything from like canceling an n plus 2 factorial with an n plus 1 factorial, like just trying to cancel it out to like a 2. Like I've seen that. I've seen attempts to expand it, like actually expand it all the way and come up with these like monstrous expressions and try to cancel it out that way. It's just a nightmare. Just take some time and try to understand why we're able to do things like this. And honestly, it starts with numerical examples. If you can do that, then it goes a long way. The root test is much easier, which is why I don't feel bad about throwing it on at the end here. Usually applies when variable power in the numerator and denominator, but also it has to be nth rootable. All right. So you're not going to see cases where there's a factorial involved, because you can't easily take the nth root of something that is in factorial form. Right? There are exceptions to everything, but generally what would have to happen is you'd have to have an nth power both top and bottom of a fraction, or it would have to simplify in such a way that an nth power would emerge in the top and bottom of a fraction. If that happens, it's very simple. What you're going to do is take the nth root, the absolute value, and then find the limit. All right, so first we identify the a sub n, the absolute value of a sub n in limit form. Now, just a quick aside here, the nth root, yeah, that's a nice way of writing it. It's concise, it's good looking, I guess. Great way to stay in shape. But you're better off writing it like this. A sub n to the 1 over n power. And that's going to do a lot more for you, I think. So we're looking at e to the 2n over n to the n, raised to the 1/nth power. One of the properties of exponents tells us that if you have a power multiply, or power to a power, you're going to multiply the powers. All right, so this ends up being e to the second over n. All right, 2n times 1 over n is going to go to 2, and n times 1 over n is going to go to 1. All right, this is the same as saying the absolute value of the limit as n approaches infinity of e squared over n, which is the absolute value of what? 0. Yeah, e squared is a constant. So constant over infinity is going to go to 0. So this is going to end up amounting to equal 0. And one thing that's consistent between the ratio test and the root test is really the conditions. If your limit is less than 1, it's going to converge just like the ratio test, and if it's more than 1, it's going to diverge just like the ratio test. So therefore, converges by the root test and again, that's because the limit is less than 1. All right, and so as you suspected, I'm going to pop a star on the second one. Second one's actually easier. I don't know if anybody claimed, honestly I can't remember if anybody claimed this typo, but that spacing just bothers me. So submit it. If somebody already has it, then you're out of luck, but you never know. Right? But if you see it anywhere else, that absurd spacing, that's a typo.